Hello and welcome to the first part of the VR character series, where we will be creating a smooth collision system for your VR character. Before we start, let's change some important settings. First, in your project, go to the plugins and enable the OpenXR plugin. Don't restart the editor yet. Then go to the project settings and go to the section called Rendering. Under Global Illumination and Reflection Method, turn off Lumen. Also, turn off Use Hardware Ray Tracing when available and Ray Trace Translucent Refractions, since these features are usually too performance heavy for VR. Change the Shadow Map method from Virtual Shadow Maps to Shadow Maps. Turn off Support Hardware Ray Tracing and Nanite. Enable Allow Static Lighting and Forward Shading. Then restart the editor. Now that everything is set up, let's create a new folder called Blueprint. In that folder, create a new blueprint of type character. I will call it BP_VR character. Before we begin adding any logic, we will need to add some components. First, let's add a new scene component and call it VR Origin. Then, add a camera and two motion controller components as children to the VR Origin. Select the right motion controller, go to the Details panel on the right and search for Source. Then, change the motion source to right. After setting up the character's components, begin by creating a new function called Calculate HMD Offset. You don't have to create functions, however, it can be difficult to keep a good overview when doing everything in the same graph. In that function, get the location of the camera and the capsule component. Then subtract the position of the capsule component from the location of the camera. Under Variables, create a new variable of type vector and call it HMD Offset. Next, create another function called Apply XY Offset. Get the capsule component and add the HMD offset to its X and Y location. Also make sure to tick the sweep checkbox. Next, get the VR origin, invert the HMD offset by multiplying by -1 and do the same but without ticking the sweep checkbox. At last, set the C location of the VR origin to the floor by getting the location of the capsule component and subtracting its half height from its C location. The X and Y location should stay the same. If you want additional control over the player's height, you can add a body C offset and add it to the new Z value of the VR origin. This variable can be useful for switching to seated gameplay or other manual floor adjustments by the player. At last, we want to apply a Z offset based on if the player is trying to stick his head through the roof or floor. Make sure to call the Calculate HMD Offset, Apply XY Offset, and Apply Z Offset functions in the event tick of your character. Create a new function called Apply Z Offset. In that function, create and call 4 new functions called Check Bottom, Calculate Half Height, Check Top, and Update Mesh Location and Rotation. In Check Bottom, get the camera and capsule components. Get the wall location of each component, split the vector pin and subtract the capsule C location from the camera C location. Store this value in a new local variable called Camera Height Offset. You don't have to create the local variable, but since we will be using this value twice in this function, we only need to calculate it once to save some performance. Next, check if the value is less than 0, and if it is, add the negated Camera Height Offset to the VR origin component. This is to prevent the player from sticking his head through the ground. Next, let's calculate the half height of the capsule component based on the camera's height. First, get the camera's wall location and split the vector pin and do the same for the capsule component. Then subtract the floor C location from the camera's C location. You can calculate the floor by subtracting the capsule half height from the capsule's C location. Then add the capsule's radius. We do this to keep the same distance to the roof as to the walls, and because in real life your eyes are usually not the highest point of your head. Now we have the full height of the new capsule, so all we need to do is to divide it by 2 and then set the capsule's new half height. Next up, the Check Top function. First, let's add a sequence and connect a line trace by channel node to the first output. Get the capsule component and its world location and radius. Then, get the camera's world location and split the vector pin. The start of the line trace is at the capsule's location. Split the end trace vector pin, break the capsule's world location vector, and connect the X and Y coordinate. For the Z coordinate, we first add the capsule radius to the camera's Z location before connecting it. You can also trace by profile or something other than the visibility channel if the trace interferes with grabbed items. Check if the trace was a hit. If it was, break the hit result, get the distance, subtract 0.1 from it, and set it as the new capsule's half height. We subtract 0.1 to not get stuck when scraping our head on the roof. Then we need to break the location vector of the hit result, get the camera's location and the capsule's radius. First, we add the radius to the camera's Z location, then we subtract it from the hit result's Z location and offset the VR origin by that amount. This will push the camera down when colliding with the roof to stop the player from sticking his head through. As you can see, this already works great. However, if the player stands up while he is underneath the roof and tries to walk out of it, he gets stuck. This happens because the capsule component no longer thinks the player is hitting his head, and when adjusting its half height, he gets stuck in the ground until the player crouches again. To combat this, we go back to the sequence node and add another line trace by channel to its second output. The trace starting location is again the capsule's world location. The trace end location is where the capsule thinks the floor is, so use the capsule's XY coordinates and subtract the half height from its Z location. If we do have a hit, this means the capsule is stuck in the ground, so we want to get the distance of the hit result. Subtract 0.1 from it to not get stuck, and set it as the capsule's new half height. The last thing we need to do is to make sure that the mesh always stays on the floor, even if the capsule's half height changes. In the update mesh location and rotation function, set the mesh's world location to the capsule's X and Y location. For the Z location, we subtract again the half height from the capsule's Z location. The great part of this system is you don't need the VR headset to test it. Simply select the camera and move it around. This simulates you controlling the camera through a VR headset. Finally, we always want the mesh to point in the direction of where the player is looking. To do this, we set the mesh's world rotation to the camera's jaw but keep its pitch and roll. If you're planning on using the UE5 Mani skeletal mesh, you need to subtract 90 degrees from the camera's jaw axis. I will show you how to set up a full-body skeletal mesh in the next part of this series. Before I end this video, we will also set up a basic movement input for our VR character. You can still use the default character movement component to move your character. Right-click in the content browser, go to Input and select Input Mapping Context. To add a new binding, you first need to create an input action under the same input category. Let's call it IA_move. Change its value type to Axis 2D. Go to the created input mapping context, select the plus icon and select the created IA_move input action. Assign the left thumbstick or trackpad to the axis of your preferred motion controller. Go back to your character blueprint and get the begin play event. Also get the player controller and its enhanced input local player subsystem and call the node add mapping context. Select your created mapping context. Call the IA_move input event and split the vector 2D action value. Add two add movement input nodes. If you want to steer your character by camera, get the camera component, otherwise get the left motion controller. Get the forward and right vector and normalize both to a 2D vector. Connect the action Y value to the first movement input together with the normalized 2D forward vector. Do the same with the right vector and the action X value. We will be expanding on the movement system in a future video. Before you can test your VR character, you have to create a game mode. In that game mode, set the default pawn class to your VR character. Then, go to the settings, maps and modes and change the default game mode to your newly created game mode. Now you're ready to test your character. If this tutorial was helpful to you, consider leaving a like and subscribe. Let me know in the comments if you need any help, and I will see you next time. Bye!